how to do the modal analysis in Abaqus. So I have just imported the INP file which I have used in my previous video, and then uh, just going to delete this, just going to modify this load step. As you can see that this load step card is of linear static. So as we can see that, as we already know that the modal analysis is used to extract the frequency and the mode shapes of the structure. So firstly, we will perform the constraint modal analysis where we are fixing it here and then obtaining the natural frequency and mode shapes. So just I'm going to double click this. Just type the name. I will type modal analysis. And in Abaqus, the modal analysis is called the frequency extraction. So analysis procedure, I will keep frequency here. And by default, it will give me Lanczos, that there are three ways to extract the modal frequency, but most commonly used in Lanczos. And then normalization, you can keep it blank, or the normalization is basically nothing but how your eigenvectors, that is your displacement, is going to vary. So if I choose displacement, the maximum displacement is going to be 1 mm, and if I choose mass, that will obtain the displacement in normalized mass. So anyways, we will keep it default. Then frequency sim, we are going to use the modern architecture, so just you put it yes. This damping projection is nothing but like if you are solving in modal FRF, then it is useful. For time being, we will keep it off, or if you keep it on also, it doesn't matter. So number of interval, these things, let it be default. Now we can define the number of eigenvalues. That means the number of frequencies you want it, or we can also set the minimum or maximum frequency. And so I want to extract, suppose 20 natural modes here, just 20 natural modes. Other things you can keep uh, as it is, no need to do this. And now you can see here in Q, this load is there. So we can keep the load as it is if you want it, because the modal analysis doesn't consider your load. If you see the equation of modal analysis, this is the equation of modal analysis, and there is no force term in modal analysis. So this doesn't consider load even if you apply the loads. But for time being, I will just delete this loads. So we can go to here, analyze, and I can just, okay, I can just delete this C load here. Just delete this load, and then output blocks, I can go on here to output blocks, and I want the displacement, stress, and if you want some other things, you can just put here too. And now stress, and I want it strain energy. So strain energy is nothing but ESC here. Okay, strain energy is nothing but SE here. So strain energy, and if you want the any other things, you can output it here, and we will just export this dashboard. This is a constraint modal analysis. Constraint modal analysis, and let me just export this. And if I see this, okay, so you will able to find these things like what it has done. So star step, it has the beginning of a step, and name whatever we are calling it as modal analysis. And perturbation, we don't need this card, we are using it for linear statics, so we can just delete this here. And then star frequency, eigen solver is Lanczos, and sim is equal to yes, which is modern architecture, so let it be. And star boundary fixed, so we are fixing it here. If you see, we are fixing it here. So we are an output block field element output S and SE. We are just here doing it, and number of modes we are calling it for 20 here. So we can just save this and we can just solve it. Let's solve this. So once this job is completed, you can see this is completed here. And if you see this message file, there is something going on with the message file here. And I will also open my DAX file here. So it has in the dat file you can see in the message file you can see that your analysis has been completed and your eigenvalues are written here. The same eigenvalues are here. So the solver basically only evaluate the eigenvalues, and then this is eigenvalue. So if you see this eigenvalue is nothing but omega square. So if you see this 6.6597, if you square root of this, you will find out this is omega, which is nothing but radians per second. And if you further want to find out the in hertz, that is the frequency, you just need to divide by 2 and divide by 3.14, which is nothing but pi. You will get this value. So this is same for every this 20 modes. And participation factor, if you see this one, this is nothing but how your modes are going to participate. The more the value, the more dominating in that mode is going to be in that direction. So if we can see that the first mode is going to dominate in the rotation of X, we will just check this in HyperView. So into Abaqus, this I can just put the INP file. So for modal analysis, I can use this modal animation, and just I will select this and see. So if you see this, just put here. So if you see this, uh, like this is dominating in about x-axis, and if we see the second, it is going to dominate in the y rotation, EY, second one. So if you see this, it is going to dominate in y-axis. And let me just randomly pick any displacement one. So currently there are no displacement one. Let me check this 12 mode number, which is going to be about x rotation. So 12th, yeah, so this is about x axis. The deformation is mostly about x axis. And yeah, so this is the modal analysis. You can plot the displacement here, and you can plot also the strain energy if you want it. So this is the constraint modal analysis. Let me just quickly, without going to the HyperMesh, I will just run the free modal analysis. So free modal analysis is nothing but your modal extraction of frequency without constraining anywhere. So I'm just going to do this. So I'm not putting any boundary conditions here. Let's see whether this is working or not. Okay, it has completed. So just we will open this ODB file here for the comparison purpose. And by the way, just I will open the dat file also of the free run to show you like you are in a free run uh, your first six modes are going to be absolutely zero. That means because those will be your rigid body modes. I will show you what a rigid body modes means. Those are simply zero frequency modes. That's why it is showing as zero. Like if you see here, sorry, you see first mode, it is basically rotating without any deformation. If you see here, uh, if you see this stress, there will be absolutely no stress here. It is very low. And up to sixth mode, this is the same story. Like it is going to just doing some free body motion. And if you see from the fifth, seventh mode, it is going to have some significant stress if you see, compare from sixth mode to the seventh mode, which is the flexible mode. So this is a flexible mode and it is going to have some stress. And if this is unconnected, then it can have like more than six rigid body modes. But it is a single body, means everything is connected and there is no mechanism, then it can have only six rigid body modes without any constraint. So yeah, let me just clear the contour and compare it with its first mode. So you can see that by constraining it here, first mode is decreased from 5.4 hertz to zero point 0.4 hertz. And there you go, like both unconstrained mode, free modal analysis and constrained modal analysis in Abaqus. One more thing here is like if you see the open the dat file here, you can see like these are marked with a star. That means these are rigid body modes. And again, like if you do the calculation again, the square root of this is nothing but this, and divided by 2 pi is nothing but this. So that's how any solver calculates uh, the modal frequency. And so this displacement and stresses are of like no use. The absolute value, the relative value are of importance. And so you can download this INP file from the description. And thank you. Have a great day. Bye.